6.0 Algebraic Models Introduction. The first topic that we're going to learn is square roots. The square of a number is the number multiplied by itself. Example, 1 squared is 1 times 1, which is 1. 2 squared is 2 times 2, which is 4, and so on. It's helpful to have each of these different products memorized through practice, because then for our square root, whenever we have a whole number answer, it's easy to evaluate. The square root of A is equal to B if B times B is equal to A. Meaning if you square that number and it gives you A, then it's the square root of A. For example, the square root of 1 is 1 because 1 times 1 is 1. The square root of 4 is 2 because 2 times 2 is 4, and so on. Next topic, solving linear equations. To solve linear equations, you must apply inverse operations on both sides. So the inverse operations include addition and subtraction as opposites, multiplication and division are opposites, and square roots are opposite. Let's take a look at some examples. 2x plus 1 is equal to 7. If we want to isolate this variable x, we have to make sure that it's the only term on this side of the equation. So we need to get rid of this term first. The opposite of adding 1 is subtracting 1, because that will result in 0 on this left-hand side. So notice that I'm showing in red subtraction of 1 on each side at the exact same time. Some people like to think of it as moving that 1 to the opposite side and it becomes negative, but it's helpful if you have a strong foundation in understanding that you are using and applying opposite operations. Next, we have 2x is equal to 6 by evaluating the previous line. When we have a term just by itself, and we have the coefficient, the number out front, times the variable, what we can do is the opposite operation. Multiplication by 2, the opposite is division by 2. So notice it's both sides of the equation divided by 2 at the exact same time. 2 divided by 2 is 1. So that means that we can just express this as x, because the coefficient of 1 does not need to be written because it is assumed. 1x is equal to 3. And if you wanted to check that your answer works, what you need to do is substitute into the equation. What we're doing is finding a solution to this equation. So 2 times 3 is 6, and 6 plus 1 is 7. So it is the correct solution. Next. In this example, notice that there are two variables. There's x on the left-hand side and x on the right-hand side. And what you can do is take all of the variables over to one side of the equation and all of the constants, the numbers just by themselves, like 3 and 9 in this instance, over to the right-hand side. But I'm going to do this piece by piece so that you can see that this is actually opposite operations working. I want to get this negative 2x over to the left-hand side. We can think of this as the operation subtraction, and the opposite of that is addition. So we'll add 2x to this side. And if we do it to the right-hand side, we have to do it to the left-hand side. Both sides at the same time. And minus 2x plus 2x is equal to 0. So we'll be left with just 9. When we add 2x to 7x, we have 9x. So we just add the coefficient. The variable stays the same for the operations addition and subtraction. Next, we have 9x plus 3 is equal to 9. So as we said, we're trying to move all of the variables to the left-hand side and all of the constants to the right-hand side. So this constant on the left-hand side must be moved over to the right-hand side. And what we can do is subtract 3 from each side. So 3 minus 3 is equal to 0. We've eliminated that constant on the left-hand side. And 9 minus 3 is 6. Now, I'm not expecting that you show these opposite operations every single time, but if you're getting a different answer than the solution, falling back on the fundamentals will be very helpful. 9x is equal to 6. We now have one term on the left-hand side, and we need to isolate our variable. We have 9 times our variable, so the opposite operation is division. Divide each side by 9 gives us x is equal to 2/3 when we reduce this fraction by dividing by 3. Again, we could check our solution. This one's a little bit more challenging, multiplying by 2/3 every time that we have x, or substituting. Next, evaluating powers with integer exponents. So what we're going to do is look at each of these exponent laws. If we have repeated multiplication of the same term, we can express that as an exponent. It allows us to express repeated multiplication. Next, the zero exponent law. Every base raised to the power 0 is equal to 1, except for when the base is 0. That would be 0 to the exponent 0, which is undefined. Negative integer exponent. So what we can do whenever we have a negative exponent is take the reciprocal of the base. So if it's a over 1, it becomes 1 over a, and raise it to the positive power n. Example, 3 to the power 4 is equal to 3 times 3 times 3 times 3. If we have just brackets, we can assume that that's multiplication as the operation, and our value is 81. 2 to the negative 5. We take the reciprocal of the base. 2 over 1 now becomes 1 over 2. And we'll raise that to the power 5. Notice that even that the numerator was raised to the power 5. 1 to the power 5 is equal to 1. Negative 5 to the power 0. Well, anything to the power 0 is equal to 1. So as long as this base is not equal to 0, and the exponent is not 0 at the same time, it's always equal to 1. Here's a good example of a fraction that has a value both in the numerator and denominator that's not equal to 1. 4/5 to the negative 2 becomes 5/4 to the positive 2. And now we can see that that square is applied to both the numerator and denominator. Evaluating 5 squared and 4 squared, we get 25 over 16. Lastly, negative exponent law. We take the reciprocal of the base, 0.4 over 1 becomes 1 over 0.4, and apply the positive exponent. So that's all to the power 3.